notice, and this is the typical copyright. After viewing these videos thus far on mathematics, as required by CSEC Physics syllabus, I hope that you are a little more comfortable now with physics for this examination. Remember that these are the formulae required under the 2015 CSEC Physics syllabus, and the syllabus normally runs for 10 years, after which it is revised and updated, but in terms of the formulae and graphs, even a revised syllabus will hardly have much change, if any, since these formulae are mainly based on classical or Newtonian physics. Graphs are an integral part of physics. In this video, that is Video Physics 23, I will deal with drawing typical Hooke's law graphs to demonstrate line of best fit and extrapolation. If you have a spring like this one here, and it has no weight attached to it, then the extension is 0. But if you were to add to that spring a force of 0.1 Newton, it will extend, it will stretch a little. We will call that x. And if you were to add to the same spring a force of 0.2 Newtons, it will extend a little more, and we will call that 2x, and so on. So the extension is directly proportional to the force or the weight. And from that, we derive the equation F is equal to K times X. One way of stating Hooke's law is this. If a spring is fixed at one end and a load is applied at the other end, its extension is directly proportional to the applied load, provided that its elastic limit has not been exceeded. This also applies to materials that can be stretched or compressed. For this video, we will focus on the stretched spring, as you see on the left here. In example 1, we will deal with the extension only. And in example 2, we will deal with the total length of the spring when the load is attached. Before we go on, let me explain what I mean by the term elastic limit. If a graph is plotted using extension versus weight or force, notice that it is a straight line from 0 to P, from 0 here to P up here. For this part of the graph, the elastic limit, or what is sometimes called the limit of proportionality, has not been exceeded. That is to say, if you take 2 newtons here and you get an extension of 10 millimeters, for another 2 newton here, you will get another extension of 10 millimeters, and for another 2 newton here, you will get an extension of 10 more millimeters, so that the extension is directly proportional to the applied load for that part up to P. Now, but beyond P, the elastic limit has been exceeded. That is to say, if you take another 2 newtons here, notice now you don't have 10 millimeters, you only have 6.5. And then if you take another 2 newtons here, you are moving from here to here, which is approximately 1 millimeter. And furthermore, if you take another 2 newtons here, you have absolutely no extension. So when we talk about elastic limit, if you take a spring and you stretch it a little and you allow it to go back, and it goes back to its original length, the elastic limit has not been exceeded. If you stretch it a little more, and when you let it go, it does not go back to its original length, then you would have exceeded the elastic limit of the spring. So that is what we mean by elastic limit. Now here is a Form 3 physics exam that I used to do in school on the unit limit of proportionality, one question with several parts, 40 minutes. A student fixed one end of a spring on a small nail and then attached several different weights on the other end. She measured the lengths of the spring when those weights were attached. The table below shows the weights and the corresponding lengths. At a weight of 1.2 newtons, the length of the spring was 0.070 meter, and so on until, if the weight is 6.0 newtons, the length of the spring is 0.111 meter. On the graph paper provided, the students were to label both axes, ensuring that the independent variable, which is the weight, is on the x-axis. They were to scale the x-axis such that it holds 7.0 newtons. They were to complete the box with scale and sensitivity of the x-axis. Then they were to do the same thing with the y-axis, but make sure it holds 0.160 meter, and complete the box with scale and sensitivity of the y-axis. That's the first 5 parts of the question. Continuing, accurately plot the given points, and then draw a line of best fit, but note that the last part of the line is curved. And then they were to use that graph to answer some questions. Find the length of the spring if the weight applied is 4.0 newtons, or what weight would cause the length of the spring to be 100 millimeters, and what would the length of the spring be if the weight attached was 6.8 newtons. Now notice this graph went up to 6.0 newtons, and that is why the students were told to make sure that this axis holds 7.0 newtons. And what is the length of the spring if no weight was attached? Continuing, calculate the gradient of the graph when the elastic limit has not been exceeded, that is to say along the straight line part. And they had some help. Gradient is equal to increase in y, which is the length, divide by increase in x, which is the weight. Clearly show the right angle triangle you use, how you got the increases, show your calculations for the gradient and the unit for your answer. And finally, given that F is equal to Kx, where F is the force applied, X is the extension, and K is the spring constant, use the gradient from part 12 above to determine the spring constant, and you are to give that in Newton per meter. And a hint for this last part, you have to do something about inverse. The total question carries 41 marks. At first reading, this may look difficult. If those students had 6 weeks to work on this one question, how to do every single part, then it may not be that difficult for such students. And this was the graph paper that they were given. We will return to this question after we try a somewhat simpler variation of it. A student fixed one end of a spring on a nail and then attached different weights on the other end. She measured the extension. Now notice this is extension, not length, as in the previous case. She measured the extension of the spring when those weights were attached. The table below shows the weights and the corresponding extensions. And here's the table. You have the weight at 0.0 weight. The extension is 0.0 millimeters. And so on. At 7.2 newtons, the extension is 112 millimeters. Draw a straight line. Now, this time we are told that it is a straight line graph of extension versus weight. So the extension here goes on the y-axis and weight goes on the x-axis. After that, calculate the gradient of this graph, clearly stating its unit of measurement. And thirdly, given that F is equal to Kx, where F is the applied force, X is the extension, and K is the spring constant, use the gradient from part 3 above, that would be part 2 above, to determine the spring constant K in newtons per meter. Now, before we get to that, let's consider also the expression line of best fit. We have used this concept before in video physics 21 in calculating half-life from a decay curve. So this is what we looked at. Those are the points. And this is the line of best fit. In this case, the line was a smooth curve, missing one or more points on both sides. And this is the computer-generated version of that same graph. As you can see, some points were missed, that one and this one below, that one above the line, and that one above the line, and that one slightly above the line. But this is a computer-generated line of best fit. And of course, once we get a graph, we use it to find certain things. Now we will see how this works with straight lines. We have the points, and the points all line up on a straight line. If you were drawing this, you would make sure that this solid line here that you see up there, for which you have data, that your graph does not exceed or go outside of those. So we are starting at maybe 10 and we are going to 100. We cannot project a solid line this way. We cannot do that, nor that way. We can't project a solid line. However, we can project a dashed line, but not a solid line because we don't have data for that. So if all the points line up like this, we get an R² value of 1.00. I will explain what this R² mean as we go along. So in this first example, the R² value is 1.00, which means that all the points line up on a single straight line. Now, if you have some points that do not line up, like that one and this one down here, we still have a line of best fit, but because these points are a little off, now the R² value is 0.997. So it drops a little from a perfect 1.00 to 0.997. And then if we have some points that are even further apart, like those on that side and these on this side, and so on, this is still our line of best fit, but now notice that the R² value decreases even further. So we now have 0.985. Note also that it does not matter how many points are missed on either side of the line. What matters is the total perpendicular distance of the points on both sides, which should be the same. So if you measure from here to there, and from here to there, we take that total, we should get about the same measurement from here to there on the other side, plus that little piece there, plus this little piece here, plus this other little piece here. It doesn't matter how many points you miss on either side. Of course, you must miss at least 1 point on either side. What matters is the total perpendicular distance from the line on both sides should be about the same. Now we have 3 points on that side, and we have 1, 2, 3, 4, 5 points on this side. Again, it is a total perpendicular distance from the line of best fit of the points on either side. And so now we have an R squared value of 0.981. 0.981, as the point starts to spread out a little more from this line of best fit. This R squared value decreases from 1. We had 0.997, 0.985, 0.981. And then if we look at another example where these points are now a little further, we only have 2 points on that side. The total distance from here to here and from here to here should be about the same as that distance plus this one, plus this one, plus that little bit there, plus this one here, plus that one there. And now we have an R squared value of 0.942. And we will look at one more example. Now, in this case, the points are even further away. If we look at the total perpendicular distance on both sides of all the points missed, they should be about the same. However, they are spread out wider than the previous ones. And so we have now an R squared value of 0.87. 0.87. So I think you should get the idea what we mean by this R squared value. We can think of this line of best fit as the average or the mean of all of those points. And we can also think of the R squared value, how much they spread out, as what we will learn about as a standard deviation. So R squared, also known as coefficient of determination, is a statistical measure that shows how well a regression model fits data. Okay, don't bother about all of that. What you need to know is it is a number that ranges from 0 to 1, with 1 indicating a perfect fit and 0 being the worst case scenario. You don't have to know how to calculate R square value. You don't even need to know what it is. All you need to know is that if you have a R square value that is close to 1 and one that is further from 1, like this one here, which is very close to 1, and this one here, which is further away from 1, that this fifth one here, the points are spread out more from the line of best fit than this one here, where the points are closer to the line of best fit. That's all you need to know about R squared value. So as I said, think of line of best fit as the average or the mean of all of those points. And also, you can think of the R squared value as the standard deviation in statistics. Standard deviation, you also need to know about that for your math CXC. But I'm using it here to help you to explain the R squared value and what it means. Now, this is part of the current CXC math syllabus. You will notice up here, now this is part 5, statistics, objective 8. It says that you should be able to use standard deviation to compare sets of data. That's for the math syllabus. And it further says that no calculation of standard deviation will be required in your math class. So much less for physics. However, it's not that difficult to calculate. This formula here may look kind of complicated, but it's fairly simple to use. But you don't even have to do it for the math class. So I'm using it in the physics class just to explain R squared value. Let us say you have 10 students in a class and they all did an exam for 100 marks and every single one of them got 50 marks each. Now, that's not likely, but let us say it happens. So the average would be 50 and the standard deviation would be 0. That is to say, if we were to draw two axes like this and we put this as the average, which is 50, you would notice that there are actually no spread out. Every single mark is exactly 50. Therefore, the standard deviation and the average, they all fall on the same line. Compare that with this. If I decrease that 50 to 40 and increase this 50 to 60, now our lowest mark is 40 and our highest mark is 60. We still have an average of 50, but notice the marks spread out a little. And this is called the standard deviation, which is 4.7 in this case, which is this blue line here. It spreads out a little from the original 50 average that we had here. And furthermore, if we were to use this same data here, but now decrease that to 30 and increase this to 70, so our lowest mark is now 30 and our highest mark is 70, and the rest of the marks are 50. Notice that our average is still 50, and now the standard deviation is 10.5. So the marks spread out a little more, as in the case of this green line here. And then we come to the last example. If we keep all of those the same as over on the left here, and we decrease that 50 to 25 and increase this 50 to 75, now our lowest mark is 25 and our highest mark is 72, and we have those 50s in there and so on. At this point, the average is basically the same 50, 49.7, but now the standard deviation is 15.3. So the marks spread out a little more, as you could see here in this yellow line. So according to your math syllabus, all you need to know about standard deviation, if you have some numbers and you find that their standard deviation is 4.7, and you have some other numbers and their standard deviation is 10.5, then the one that has standard deviation of 10.5, that those numbers are spread out wider than the one that has standard deviation of 4.7. 4.7, it does not spread out. The marks do not spread out as much as in 10.5. So as I said, think of the line of best fit as the average of those points and the R squared value somewhat similar to the standard deviation of a set of numbers. An R squared value of 1.000 means that all the points are lined up, and as the R squared value decreases from 1, the points spread out further away from the line of best fit. Well, we have seen this before. All you need to know is it goes from 0 to 1, with 1 indicating a perfect fit. And as I said, you don't need to know this for CSEC, physics, nor even for mathematics. But you do need to have a little idea of what R square value is. If you find this video useful, please like, share, and subscribe to this channel. To further explain what is happening here, unlike what happens in algebra, where you use an equation to get coordinates to plot a graph, in science, especially physics, the data may have errors when measurements are taken. You already know that there are two categories of errors: random errors, and these are errors caused by the people taking the measurement. Example, reaction time errors and error of parallax. And then the second category, which would be systematic errors, and these are caused by problems with the instrument. And you have two such examples are incorrect calibration and zero error. Now, systematic errors will be consistently too low or too high, so these may not cause much of a problem for a graph. However, if the instrument is erratic, now we will have some systematic errors as well. Anyway, hardly ever do the points all line up for graphs in physics, so we have to deal with it. Now, in algebra, as you know, you may have an equation like that and you're asked to plot it on a graph. So you take some x values, you find the corresponding y values, and you plot it, and you come up with this. Notice that all the points are lined up on the graph. All the points are lined up. That is because you began with an equation. Or that was a straight line equation. Now you have a quadratic equation here. Same thing. All the points line up smoothly with a graph, or rather the line touches all the points smoothly. Or even if you take an example like this, and here we know we have two lines on the same graph. You have this one here, which is xy is equal to 27, and you have this one here, which is y is equal to x plus 3. But notice again, the line pass through every single point. Or even take this example, which has to do with business, supply and demand. Again, you began with two equations. You get the corresponding points over here. You plot them. Notice again that all the points line up in the case of a straight line or a curved line. By the way, this is called linear programming, and you will meet this for mathematics CSEC. That is what happens in algebra, but not so in physics because of those errors we mentioned earlier. So what do? We draw a line of best fit, and it is determined by its goodness of fit using the R squared concept. That is to say, how good the points fit in relation to the line. Now, R squared is also called the coefficient of determination. Remember, you don't need to calculate this, and you don't even have to define it. But you do need to have an idea that if one graph has an R squared value of 0.8, another one has an R squared value of 0.9, the one with 0.9, the points are closer together to the graph than the one with 0.8. If all the points line up, as we said, the R squared value is 1. The value drops off as the points become more disorganized or further away from the graph, and it could go right down to 0.0. These R squared values are said to give the proportion of variance. Again, you don't need to know that. For CSEC physics, you do not need to know anything about R squared variance of graph. I am introducing them here to help you understand how to draw lines of best fit. So in algebra, we begin with a formula or an equation, and then we draw a graph from it. But in physics, we begin by drawing a graph, which is a line of best fit, from data points, and then we derive a formula or an equation from the graph, such as PV is equal to C. You don't have to do this at this stage in physics. One other concept the idea of extrapolation. Now, in general usage, extrapolation means the action of estimating or concluding something by assuming that existing trends will continue or a current method will remain applicable. That is one definition of extrapolation, the general definition. As it applies to mathematics, it is the extension of a graph, a curve, or a range of values, inferring unknown values from trends in the known data. That's extrapolation. And that definition is taken from Oxford University Press Online Dictionary. Now, for those of us who believe in a theistic God, example Christians, this is as good a definition of faith as any. It is an extrapolation of known data, including inference to the best explanation. We are in good company. That is the same definition that Sir Isaac Newton used when he looked at the solar system and concluded that it actually required an intelligent designer to set up our solar system. So our scientific definition of faith is an extrapolation of known data, and that includes inference to the best explanation. And it is not blind faith as we are sometimes accused of.